Alright, welcome to section 11.10. So we're heading into our last major topic of the course. We've got two more sections. This one's going to be part one of this section, and then we'll have part two right after this. It's a little bit longer of a section. So we're talking about Taylor and Maclaurin series. So in this section, we're going to be asking the questions, which functions have power series representations? And how can we find such representations? So suppose that f is any function that can be represented by a power series. Okay, so if f of x equals that power series, let's figure out what the coefficients c sub n must be in terms of f. So we're trying to figure out if we have a function that we suppose can be represented by a power series, what are those coefficients in terms of function values? How can we get those? So notice, if we have x equal to a, then all the terms after the first one are 0. So we would get f of a equals c sub 0. We can differentiate that first series term by term. That gives us f prime of x equals c1 plus 2c2 times x minus a, etc., just the derivative. And substitution of x equals a gives us f prime of a equals c1, because all the additional terms turn into zeros. Differentiate again to get f double prime of x, and then using x equals a again gives us f double prime of a equals 2c2. Okay, and then let's do this even one more time. So differentiate again, get f triple prime. So substitute x equals a, and we get f triple prime of a equals 2 times 3 times c3. Now, if you look at all these coefficients here, you might notice a pattern starting to appear, but this is actually the same thing as 3 factorial times c sub 3. And if you can start recognizing the pattern here, so with every derivative that we take, we start picking up those additional terms on the front being multiplied. So we can, if we continue to differentiate this, we're going to see that the fourth derivative gives us 4 factorial c4. Fifth derivative is 5 factorial c5, etc. So the nth derivative at a would give us 2 times 3 times 4 times etc. all the way up to n times c sub n, that nth coefficient. And this is just equal to n factorial times c sub n. Okay, solving this for the coefficient, because again that's what we're looking for, is how do we get that coefficient. We get the coefficient, the nth coefficient is the nth derivative at a over n factorial. Okay, so we get that any nth coefficient of this series is going to be the nth derivative at a over n factorial. And this also holds for n equals 0, because 0 factorial is 1, and the 0th derivative of f is just f, because if you haven't taken a derivative, right, that's just the original function. So, all right. So this section has a lot of theorems, a lot of information that we're kind of getting to here. So here's a theorem: if f has a power series representation or expansion at a, so that is the function f can be written as a power series, right? We saw that in the last couple sections. Then its coefficients are given by that formula that we just established. Okay? Substituting this formula in for the coefficients, this gives us the power series expansion of f at a. Okay, so we have here, right, instead of using c now, we're using this expression in terms of the function and its derivatives, right? So that gives us, right, f of a plus f prime of a over 1 factorial times x minus a, f double prime at a over 2 factorial times x minus a squared, right? And the power series is counting up, and so are the derivatives and the factorials. This series is called the Taylor series of the function f at a. All right, so the Taylor series of the function gives us this series of terms with the derivative values and the factorials instead of the arbitrary c sub n values. Okay. And for the special case where a equals 0, we get this series down here, f of 0 plus f prime of 0 over 1 factorial times x, right? So basically the minus a's all go away, and then that pattern just continues. This one occurs frequently enough that it gets its own name, and this is the Maclaurin series. Okay, which the name is a little bit deceptive because Maclaurin did not create this series, actually Taylor did. But Maclaurin was the one who then popularized the use of this series a little bit after that in his own publication. So he gets kind of the namesake of this one. But this one comes up frequently enough using a equals 0 that we do kind of separate it apart from the other one. Okay, so again, the Taylor series is this one up here. The Maclaurin series is just a special case of a Taylor series where a equals 0. Okay, so that's the only difference between the two of them. So if f can be represented as a power series about a, then f is equal to the sum of its Taylor series, but not all functions have this property. Okay, so let me say that one more time. So if f can be represented as a power series about a, then f is equal to the sum of its Taylor series. Okay, but not all functions have this property, right? Because not all functions can be represented as power series. So we're going to be looking at some functions that we can do this with, and we're going to do a couple of proofs as well to demonstrate that they are equal to the sum of their Taylor series, not just represented by that power series. Okay, so first up, find the Maclaurin series of the function f of x equals e to the x and its radius of convergence. So let's start off here establishing some values. So if the function in question, if f of x equals e to the x, then the nth derivative, whatever that may be, is just going to be e to the x, right? Because the derivative of e to the x is e to the x. No matter how many derivatives you take, that's not going to change. So the nth derivative at 0 will always be e to the 0, which is 1, for all n. Okay, so for all values of n. So thus, the Maclaurin series is the sum with n going from 0 to infinity, right, of the nth derivative at 0 over n factorial times x to the n, which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Okay. So that is the Maclaurin series for e to the x. Okay, 1 plus x over 1 factorial plus x squared over 2 factorial, etc. So to find r, so that radius of convergence, so to find r, we are going to use the ratio test like we have in the past. Let a sub n be x to the n over n factorial. Then we're going to have the following. So we have, right, that ratio a sub n plus 1 over a sub n. That's going to be x to the n plus 1 over n plus 1 factorial. times n factorial over x to the n, right? Multiplication by the reciprocal. Cancel where we can. That leaves us with absolute value of x over n plus 1, which heads to 0, right, as n goes towards infinity, which is less than 1, okay, which is what we need for the ratio test. So, by the ratio test, the series converges for all x. Alright, so the series converges for all x. So we get r equals infinity. Alright, so it's convergent for all values. Okay, so now let's go ahead and we're going to get into a little more kind of heavy theoretical stuff here, but this is going to lead us into kind of the rest of the section where we can start making these representations and verifying that they give us exact values for the function. So let's look first at the partial sums of the Taylor series. Remember, the partial sums of a series are just all of the terms up to the nth term, and these are considered finite, right? Because then you can let the limit go off towards infinity. But the partial sums themselves are just finite up until n. So the partial sums of the Taylor series, we use t sub n to represent these. So that's going to be just the same relationship, but with I going from 0 to n, because again, it's finite, so it's not n going to infinity. But we have the ith derivative at a over I factorial times x minus a to the ith power. Okay, so we write out that expansion, and this is a polynomial of degree n. So we call Tn, or T sub n, the nth degree Taylor polynomial of f at a. Emphasis on Taylor polynomial. So when we talk about the Taylor polynomial, we're talking about not the entire series, but just one finite piece of it up until n, whatever n may be, right? 1, 2, 3, 4, however many. Okay? So for example, for the case of e to the x, if we look at the Taylor polynomials at 0 for e to the x with n equals 1, 2, and 3, we get the following functions. Okay, so there's our first partial sum, then our next one, and then our last one over here. Okay, so we get three partial sums that are all increasing in number of terms, right? We could get the fourth, the fifth, etc. if we wanted to. And now let's look at what's happening on the graphs of these functions. So here's the graph of e to the x. Now if I graph t1, right, that first partial sum, it doesn't really do much for us, right? That's just a line. If I go ahead and graph the second partial sum, notice that is parabolic, but it's starting to get a little closer to mirroring the e function. The third one, you can see if I get rid of those two, is getting even closer to approximating e to the x. If you keep going, it turns out that you get approximations that are closer and closer and closer to the actual function value. Okay? So the nth Taylor polynomial is, as n goes towards infinity, that's going to get closer and closer to the actual curve, right, and the actual function values that we're looking for. And that's the idea here, is we're trying to get values of these functions as exactly as we can using a series, instead of just looking at the function directly. So in general, f of x is the sum of its Taylor series if f of x equals the limit of the Taylor polynomials. Okay, so again, like I said, the Taylor polynomials, as n goes towards infinity, they're going to get closer and closer to the function. So we say f of x is the sum of its Taylor series if that is the case. if they actually do head towards the function. This is equivalent to saying that the remainder of the Taylor series R sub n which is equal to f minus t. Okay, so the remainder is just the function minus our approximation. That tells you how much is left over, kind of like error, right? How far off is our approximation from the real thing? If that satisfies the property where the remainder, as n goes towards infinity, goes to 0. So think about that. If t, our approximation, is getting closer and closer to the function, the remainder, the difference between them, should be getting closer and closer to 0. In other words, our approximation is getting better and better. There's less left over if we do a better approximation. Okay, so this brings us to kind of formally state that in this theorem. So if f of x equals the Taylor polynomial plus the remainder, where t sub n is the nth degree Taylor polynomial of f at a, and the remainder heads to 0 as n goes towards infinity, then f is equal to the sum of its Taylor series. So f is equal to the sum of its Taylor series on that interval of convergence. Okay, so this is going to allow us to say that f is equal to the sum of its Taylor series. All right, and this brings us to kind of another tool that's going to be very valuable for this process, and that is Taylor's inequality. So Taylor's inequality says if the n plus 1th derivative, if the absolute value of that is less than or equal to m, for the difference between x and a being less than or equal to d, then the remainder of the Taylor series satisfies this inequality. Okay, so m and d are constants. So m and d are constants. And we want to see that if the n plus 1th derivative is staying within a certain boundary and x is staying within a certain distance of d, then the remainder stays within this value. Okay, so we have this property. This is going to be useful, and you'll see when we do one of the proofs why this property is useful. We're not going to prove this, but this theorem will typically be used to show that that limit of the remainder is 0. Okay, because basically if we can show that that goes to 0, and this is less than or equal to that, then that's going to have to go to 0 as well, because it's an absolute value. All right. And then there's a helpful fact here for you guys. We're not going to prove this, but there's a property that is going to come in handy in some of these proofs. The limit as n approaches infinity of x to the n over n factorial equals 0. So in the long run behavior of that function x to the n over n factorial is going to end up being greater in the long run, right? Because once you pass x, then n factorial is just going to get bigger and bigger. So that is going to head to 0 for all real numbers x. All right. So let's look at this proof here. So prove that e to the x is equal to the sum of its Maclaurin series. So we already found what that series was, right? What its Maclaurin series is. But now we're actually going to prove that e to the x is equal to the sum of its Maclaurin series. So let's start off here setting up Taylor's inequality. So if f of x is e to the x, that tells us the n plus 1th derivative will always be e to the x, right, for all n. Okay. If d is any positive number, and absolute value of x is less than or equal to d, as is required, then the absolute value of that derivative, which is just going to be e to the x, right, because the derivative, any derivative is e to the x, that will be less than or equal to e to the d. Okay, so track with me here for just a second, make sure we're all on the same page here. Since the function is e to the x, any derivative of that function is e to the x. Since the absolute value of x is less than or equal to d, e to the x must be less than or equal to e to the d. Okay, because d is always going to be greater than or equal to x. So that's all we've said so far. Okay. So, now we look at Taylor's inequality. So Taylor's inequality with a equals 0, right, because it's a Maclaurin series, and choose m to be e to the d, right, and again, why we're choosing e to the d, because we want this ultimately to be bounded above by something. So that's what we're going to choose for our m value. Says that we have the absolute value of the remainder is less than or equal to e to the d, right, m, over n plus 1 factorial times the absolute value of x to the n plus 1 for the absolute value of x being less than or equal to d. Okay. Now, notice that no matter what value of n we're working with, because all those derivatives are going to be the same, they're always going to be e to the x, our value for m will always work for all n. Okay, so notice m equals e to the d works for all n. But since that's the case, when we look at this expression and we take a limit, we have the limit as n approaches infinity of e to the d over n plus 1 factorial times the absolute value of x to the n plus 1. E to the d is just a constant. We can pull it out of the limit entirely. So we just get absolute value of x to the n plus 1 over n plus 1 factorial. This comes back to this property up here. That relationship tells us this limit is going to be 0. Okay, so we're using, again, this property up here tells us that that limit is 0. But since this expression here is heading to 0, so this expression is heading to 0, and this is the absolute value of the remainder, this must be going to a smaller value than that, or equal, right? But it can't be negative, so the remainder is going to have to be 0 as well. Okay, and this is actually by a theorem from your Calc 1 days, then that's actually the squeeze theorem. So we can say, so thus, where are we going to put this? So thus, by the squeeze theorem, the limit as n goes to infinity of the absolute value of the remainder equals 0. So if the limit of the absolute value goes to 0, then that means that the remainder itself must go to 0. Okay, and this is for all x. Okay, so since the remainder is going to 0, right, the limit is 0 on the remainder, that means the remainder is heading to nothing, which means our series is heading towards e to the x, exactly. Okay, so we can conclude, thus, e to the x, I'll fill that in there in just a second, e to the x is equal to the sum of its Maclaurin series it doesn't like the word Maclaurin, huh? Try that again. Maclaurin. There we go, and this is e to the x. Okay, so thus e to the x is equal to the sum of its Maclaurin series. Okay, and then that's our proof. Okay, so we prove that not only is E represented by a Maclaurin series, but it is equal to the sum of that Maclaurin series. Okay, so we can, just kind of sum this up here. Let me just separate this off. So we can say, therefore, e to the x equals the sum, with n going from 0 to infinity, of x to the n over n factorial for all x. Okay, so this is going to give us a series that now represents all values of e to the x as long as you let n go towards infinity, right? So for example, right, if we had, right, for example, if x was 1, that would give us e equals the sum of 1 over n factorial, which is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, etc., etc. And that would give us a value that approximates e, right? The actual number e. If you wanted to find e squared, then you would choose to approximate when x is 2. And if you want to find what e cubed is, you would get the approximation when x is 3. And you could do that for any value of x that we want. Okay? Alright, so we do have plenty more examples to do in this section, but we're going to go ahead and just take a pause here, because I know I'm throwing a lot of information at you guys in this section, so we're going to take a pause. When we come back, we're going to look at a bunch more examples of finding Taylor and Maclaurin series for other functions.